So we're going to finally put all what we learned together. We've talked about all the different atmospheric variables and how they influence temperature, how they influence pressure, how they influence wind circulations, how they influence moisture. Well, we're going to take a look at the whole planet now and see if we can come up with what would be an average circulation for the planet as a whole. So, what are some of these principal features? Here's a case very quickly looking at the southern part of the Sahara. There's a belt where sometimes precipitation can come in and give a very wet climate for the summer. Sometimes it backs off. So for years, people living along this area try to have agriculture to feed their families and all. Some years, almost no rain occurs. Some years, lots of rain, very beneficial. So this is part of a setup of actual atmospheric circulation as such that sets up every year, but just with slight variations. So they've been studying this for years to try to understand how to model it, how to help the farmers know that this year is going to be a great crop or no precipitation. But they've got to look at the atmosphere as a whole again to understand all of these things. So if we had a non-rotating Earth, and guess what? Well, there are planets out there that don't rotate. So one side is getting continuous sunshine. Most of the sunshine, heaviest, most intense sunshine comes in at the equator. The other side, no sunshine. So what develops where the equator is, where the sun side is, lots of convection, gets very hot, air rises, lifts up, and guess what? It's going to sink where the coldest spot is, which is the exactly opposite side of the world. So you get two circulations. One would be the southern hemisphere, and one in the northern hemisphere. But our Earth rotates, so we know in the northern hemisphere the winds are tilted to the right, and we know in the southern hemisphere they go to the left. So we've immediately changed that circulation. And with that change, instead of one big circulation of convection belting over the equator and coming up and down on the other side, we wind up with convection does build over the equator, but it comes down right around 30 degrees north. Then it goes up again and down again, and so on, making a series of highs and low pressures across the globe. And you can see them right here. Low pressures right along 60 degrees north. A little further north than we live, but those shift a little bit with time, so we get some of that low pressure. High pressure, ever hear of Bermuda High? It's right at 30 degrees north, roughly, a little bit south of it. And that will move up north in the summertime, down south in the wintertime. And the same with low pressure over the equator, intertropical convergence zone we talk about. Continents and oceans impact these. Remember, continents heat up more than the ocean. Oceans don't cool as much in the winter as continents do. This impacts how these circulations set up as well. And if you were to look at a planetary map, average out the general circulations, this is what you would see. You would see high pressure right along 30 degrees north in the wintertime, maybe even a little bit south of that. Low pressure right there around 60 degrees north, several of them moving along there, right along the equator and out moving a little bit further south of the equator because it's January, more low pressures. And notice that the lower pressures are actually over land in the southern hemisphere where the heating's taking place. Remember, it got hotter there. In the wintertime, colder air is over the continents, so the higher pressures actually are over the continents. Siberia gets very high pressure. Winter comes back to summertime now. We move everything to the north. High pressure is now more centered over the water. Water stays cooler. Land gets warmer, so we have lower pressures over land. Intertropical convergence zone moves north. So this is the general planetary circulation. So if you were to look at the globe and say, oh, where do I live in respect to these circulations, this is what you would get for your average weather. Not daily weather, but average over time. And we can see them here on the schematic. Polar easterlies up here with low pressures moving along them, big high pressure centers over the subtropics, trade winds. All of that reflects atmospheric flow on a broad scale. If I wanted to leave like Columbus did to find the United States, where he wanted to go west, he would have started up here and moved down around these subtropical highs and take the trade wind route right across. Hopefully, he would hit the United States at some point when he was moving with his sailing ships. If you were trying to get from the United States back across, you would want to go a little further north. If, on the other hand, you wound up hitting in these high pressures, you could be sitting there for days with no wind. These subtropical anticyclones have a major influence on the climate. So, on the eastern sides, there's compressed warming. Air sinks the most. This is where most of the deserts form. The Sahara deserts on the eastern side. There's a desert over Chile, part of the eastern flank again, of subtropical high that's in the Pacific area. And right in the middle of the high is what they call the horse latitudes, because not much wind results in that area. To the north of the high, you have the mid latitudes where we live, westerlies, and then south of them, you have the trade winds. So further north now of the most subtropical highs, you have the westerly flow, and especially in our region, and you have some polar lows. They typically form the Aleutian low and the Icelandic low over the North Atlantic, and that is up around 60 degrees north, where we talk about lots of low pressures. Fronts drop down from these lows, move into the United States, and across our area. That's the mid-latitude weather we're going to talk about next week. Over the poles, there's a polar vortex. Very intense some years and not so intense other years. So you think about it. If you have circulation of air moving from the east to the west and lost big clockwise circulation there, you wind up, if it's very strong winds, not much cold air can move south. If the winds get weaker, more cold air from the Arctic can move south. So we will look at that real close to see if there's going to be Arctic outbreaks moving into the United States or not. Now back into where we talked about these different little cells, where we have rising air over the intertropical convergence zone right around the equator. Then we wind up with sinking air right around 30 degrees north. That sinking air pushes air down, increases the pressure. That's called the Hadley cell. That's the first of three cells. To the north of that, you have the westerlies, and you can see the winds blowing. Nice little wavy pattern up here. Some days the waves are more intense, some days the waves are not too much. And if I would ask you what the tropopause is doing, Hadley cell, remember lots of warm air down there, pushes the tropopause really high. Up by the poles, lots of cold air, cold almost all year long. So the tropopause is much lower there. In between, where it depends on where the polar front is as to where the tropopause is. It will oscillate with that front. So you can watch the tropopause go up and down. Some days it might be well up into the atmosphere. Other days it might be much lower. So why is there a trade wind inversion? Well, we know that the Hadley cell descends right over where the subtropical anticyclones are. When it descends, it's warming. Relative humidity is decreasing, while over the water, you have lots of moisture, coolness. So you wind up basically forming an inversion there, the trade wind inversion. This is very evident over places like Hawaii and the islands out there. And it makes a major difference on what kind of weather they have. Again, the seasons always follow the sun. If the sun is moving right now, for example, it's still heading south. So that is pushing everything towards the south. In the summertime, in the late spring or or even early spring, the sun is coming back to the north, pushing everything back. And with that, notice the temperature changes. Much further north for the warmest temperatures in July, right over India or into Asia, while over the oceans, there's not a whole lot of change. You can really see it here in the Atlantic Ocean. The intertropical convergence zone doesn't move a whole lot. Kind of the same over the Pacific. And again, this motion, though, really can impact. We know that the Bermuda High or other anticyclones on their eastern edge have a sinking motion. So the eastern edge of the Pacific anticyclone is over San Diego. So when it gets pushed north, right over the area in the summertime, like San Diego would be, almost no rain occurs. However, in the wintertime, it moves south. Then we're allowing the westerlies that are just north of there to flow in, giving significantly more precipitation to San Diego. Charleston, on the other hand, is on the opposite side of that anticyclone, Bermuda High. It has lots of moisture coming up almost year-round, but the peaks are in the summertime when it's tropical, more humid. The intertropical convergence zone's closer, the more humid air from the tropics are closer. So we wind up with more precipitation. Notice the significant difference in the amount, too. All right, because we have these semi-permanent circulations, we wind up with semi-permanent circulations in the ocean. Remember, oceans are just fluid of water, and the air begins to move them. If you keep the air motion the same over some area for hundreds of years, the water is going to begin to look the same as the airflow. Let's focus just on the North Atlantic gyre. This right here, notice the Gulf Stream coming out of the Gulf of Mexico up the east coast of the United States and right on over towards England, all influenced by the subtropical high pressure system there. If we didn't have that Gulf Stream on the east coast of the United States, we would be a lot colder because of that warm air. And also, notice that it heads to England. It keeps England warmer than it would normally be. So some of these seasonal contrasts can really create a difference in climate. For example, we saw how the warmth moved north in the summertime. Well, if it moved north in the summertime over Asia, it moves to the northern part of Asia, almost into the Himalayas there, coming up other areas into the Bay of Bengal. All of that pushes in tremendous amounts of moisture from the Indian Ocean because of where the warmth is. Air is going to be rising. So it's pulling air from the south to take that place. So you wind up with the monsoon season being very wet over parts of Southeast Asia, parts of India. Now in the wintertime, it cooled off. The air comes out of Siberia. Siberia doesn't have any moisture really. So very dry conditions set in for the wintertime. And here you can actually see that in the amount of precipitation over New Delhi. Look at all the tremendous precipitation that falls during the summertime. Temperature is much warmer until the precipitation sets in. It would continue to warm if we didn't have all the precipitation. Much drier in the winter. We actually have a monsoon circulation in the United States. Arizona and New Mexico are significantly influenced by the North American monsoon. So how does that develop? Well, first, you wind up with lots of heating in northern Mexico during May and June. Kind of almost like a desert there anyways. So the land heats up, and we know that the hotter the air is, the more it spreads out, and it spreads out, it forms low pressure. So we wind up with low pressure at the surface, and we know that when the atmosphere is warm, pressure doesn't fall as fast, so you wind up with high pressure above it. So you've created high pressure aloft and low pressure at the surface. This becomes a pretty stationary pattern. So it pulls moisture in from the Gulf of Mexico, the Gulf of California, into the central parts of Mexico there. Because of the high pressure above it, it allows divergence up there, And you wind up with thunderstorms developing. Monsoon gradually shifts north, basically over New Mexico by July, and you can see it here. All kind of moisture coming in to the southern parts this year. We even got some circulations where there was some actual hurricanes coming into this area in California, New Mexico. And what happened is they pulled the moisture up with the monsoon, dumped tremendous rainfalls in parts of Arizona, some into Las Vegas, Nevada. Tremendous flooding occurred there. And you can see the difference in precipitation. In Tucson, for example, not a whole lot in the winter, other months. But boy, when you get to July and August, it's significantly more. All right, here's where I'll show you this at the end. We're going to talk about Rossby waves, and I want to do a little bit more with that. But the westerlies are really can look like two components. There's a meridional flow and a zonal flow. So zonal flow, there's still a little curve, it's a little wavy, but it's not a lot. Meridional flow is significant, very deep, troughs, very big ridges. So what happens if you push all that cold air south and all that warm air north, you're winding up with tremendous temperature contrast here. Zonal flow, things move pretty quickly from west to east, and you don't get that strong system. Here you're going to get a much stronger system. It's a meridional flow. There's also blocking patterns. They form when maybe you get a very cold, low pressure system that has moved pretty far south, and it winds up getting cut off from the main jet stream to the north. Or the same would happen with the warm here. And they can persist for weeks sometimes. When they happen is when we get our extreme weather. Lots of rainfall, lots of snowfall, lots of cold air. And you can see here, this was in the summer of 1988. Large high pressure system over the central United States. Here would have been a normal year. There'd been some high, but not like this. What it did was tremendous drought occurred over the central United States at the time. Here, exactly the opposite occurred. That high did develop and wind up with all kind of precipitation in the central United States that year. Polar jet stream is the most prominent jet stream in the mid latitudes. So how does a polar jet stream form? Well, we learned pressure drops faster in cold air. So if you're in the cold side of a system, the pressure is going to decrease very quickly. If you're on the warm side, it's not going to decrease as fast. So what you wind up with is an extreme pressure gradient develops in the northern and the upper atmosphere, very close to where the tropopause is, where that extreme jet stream has developed, causes a jet stream, excuse me, and you wind up with strong winds up in that latitude. And the Coriolis effects balances that out. And you can see in the summertime, the jet stream, as you would expect, moves further north. In the wintertime, it moves further south. So there's another part of the jet stream we call short waves. And let's look at that in a little bit more detail here later. These all contribute to cyclone development. We're going to go into a lot of detail on that next week. So El Nino and La Nina are also features of the planetary circulation. We'll learn that El Nino basically means we have warm water over the eastern part of the Pacific. La Nina means we have cooler water. So that ENSO, the Southern Oscillation, was learned about in 1966, and we have discovered that when you go back in time, you can relate that to how weather conditions are impacted around the globe. Another impact of all of this is Ekman's spiral comes into a play. You can see that because that's where we had the gyros moving around. On the east coast of the United States, for example, if you get more southerly winds along the coast, it's going to increase the flow of water moving north. Well, the water is going to want to turn to the right, so it's moving away from the coast, and what you wind up with is the cold water coming up on the east coast of the United States because of that, from the upwelling. So this is the neutral conditions, how you would expect precipitation to occur if we had no ENSO. Notice lots of precipitation still along the Gulf Stream and along the intertropical convergence zones. More precipitation in the coming up out of the Gulf of Mexico in the Midwest. Now, this is neutral. We wind up with most of the thunderstorms in the western part of the Pacific Ocean. Nice circulation there. But El Nino, pressure begins to fall. We want to look at that here. You wind up with lots of low pressure along the equator, warm, very warm water temperatures in the eastern part. So you wind up actually pushing air up and slowing the winds. The typical trade winds that would flow here aren't as fast. La Nina is exactly the opposite. We have more trade winds, faster easterlies down low. And here we have divided the Pacific into Nino regions. Nino 3.4 is actually the region that we look at to see if we're having an El Nino or La Nina. We have what we call an ENSO alert system now, where an El Nino watch may be issued or a La Nina watch. They try to look 6 months out to issue them. Why do they issue them so early? Because these weather systems can have major impacts on agriculture, on how many storms may occur, on what parts of different areas may receive more snow or rain. This allows people to make plans and utilize this information. There's another circulation, North Atlantic Oscillation. When it's positive, you wind up with stronger than usual winter winds blowing across North America, colder air masses. Negative, you get a little bit different conditions. So you can see here, all it is the difference in pressure between near the equator and up over Iceland. The greater the difference, the more positive that would be. The less the difference, the weaker that would be. And you can see from that how it changes the east coast of the United States in particular. If we ever had a good forecast for that all winter long, we could do a much better job making wintertime forecasts. Arctic oscillation, we've talked about that. We want to know how powerful the Arctic circulation is. The more powerful it is, the less cold air from the Arctic will come into the United States. And there's your positive and negative phases and how they circulate. There's Pacific decadal oscillation as well. We have an Atlantic decadal oscillation. We also have a Pacific one. They impact some of the climate. There's another thing called Madden-Julian oscillation. What this is areas of thunderstorms develop over the tropical Indian Ocean, and they traverse to the east, running about 10 to 20 miles per hour. As they move along, they have cycles of upward motion and downward motion. And they move across the United States, and you can actually see these cycles impacting whether extratropical storms form, even in summertime, whether tropical storms form or not. And they can impact how much precipitation will come into the West Coast. So I wanted to try to show you one last thing on the jet stream. This is the current jet stream right here, and you can really see how it buckles and curves all over the place. Rossby waves are long waves. So what we're looking at here, for example, from here to here would be a Rossby wave, large part of the western United States. There's another one here in the eastern and coming over into the Greenland here. In those little areas, we have little tiny short waves, like here, for example, or another one here. There may be 3 or 4 short waves moving through a Rossby wave. They tend to deepen where the Rossby wave is deepest, and they tend to weaken or become less intense as they move out of the Rossby wave. That's all we're talking about with those. So this is a lot to cover here, I know. Hope you got something out of it. Let me know if you have any questions.